Yeah, Assalamualaikum and good afternoon, everyone. Have a blessed Ramadan. So, this is essentially my attempt to do something that wanted to be doing for a long time. So, let me just open the file. Can you see this? Okay. Maybe that would be good enough, I think. So, essentially, this is a thing that I wanted to do, as I said, to relearn some of the things that we sort of uh, um, not play what you call plays an important role in most of our research. But I think to a certain extent, I feel guilty of this and wanted to say something about it. Okay, so but let me begin with let's see how to get this thing. Yeah, let me begin with some background why I wanted to do this. One of the things, essentially, there was this book, uh, Ideas and Realities. Okay? Essentially, it's a most of the essays inside this book by Salam, actually, edited by C.H. Lai. And these are the essays are essentially non-technical, and some recollections of meeting scientists, and one of them is meeting Paul Dirac. Okay, so one of the questions that Paul Dirac asked Abdul Salam is to say what kind of research that is doing, and and essentially Abdul Salam mentions the kind of research that he's doing, and then he says, as expected, algebraic in nature and less analytical. Now, I couldn't find my book. Somebody must have borrowed this book, so I couldn't find essentially the context of this. But I guess it's nothing, it's nothing disrespectful with respect to this conversation between these two giants. Essentially, it's just a matter of the tendency of the approach that one does in, say, doing research in theoretical physics. Okay, so, and you have to remember that Dirac is known to be man of a few words, and it was quite surprising that he mentions this to Salam. So one of the questions is I always ask is why we have a tendency to do certain things, particularly emulation context. We tend to do the easy things, okay, and perhaps with respect to mathematics, we tend to appreciate less ad maths compared to modern maths or something like that. Okay, so to me, this is our weakness. Oh, by the way, please shout if you have some question. No, I couldn't see anything else apart from my screen.
Before you say, yes,
Uh,
Dirac was a Salam supervisor.
no, Sanam supervisor was, I think, relatively unknown. I think Matthews or something. I can't remember. But no, it was in Cambridge. So essentially, they get to meet each other. So where was I? Okay. So the idea is now a lot of this functional analysis part we tend to ignore because we concentrate more on the structural aspects, algebras, groups, and everything else. And to me, it's something that in the long run one should acquire some expertise inside this part of our area. I think probably Nurisha knows better than me on, but right, Narisha?
It's long time ago.
So, so the other background that I wanted to mention is the fact that what happens. The thing that I was trying to say was the fact that von Neumann actually sort of make the mathematics of quantum mechanics more rigorous in his book called Mathematical Foundations of Quantum Mechanics. Okay, and this was, I think, I think the first edition is 1932. I think the latest edition is quite recent, I think 1970s or something like that. This is the third edition. Okay, and but after that, you probably have seen this on the on the on the pages of Bob Cooker's papers. He was saying that after publishing that giant book, in some sense, Weinman expressed that he doesn't believe in Hilbert space anymore. Okay, so one of the things that I wanted to also see, I couldn't get to the point of presenting in this particular presentation, is that Weinman was actually looking for something which is more geometric. I think there was an unfinished manuscript by John Weinman, okay, who wanted to see a geometric probabilistic logic kind of approach, but he didn't get to finish that. So that was one of the things I wanted to actually have a look. Okay, before we go on to Bob Cooker's approach of using category theories. Again, these are more structures on top of structures. So you get an uneasy feeling when you always start to use all these abstract terms without really understanding some of the more basic terms. Okay. Let me go next. Oops. So this is just a slide on the postulates. Probably you have seen this many times, but I just want to explain a few things. One of the things is essentially is the idea of a state vector. It is the complete description for quantum mechanics. Okay? The state vector has to belong to an infinite dimensional Hilbert space. Okay, so despite that, in quantum info, we tend to zoom down to some finite dimensional state spaces, but that is only a subspace of this bigger infinite dimensional Hilbert space. And why is this happening? We'll see in a minute. And then, of course, once you have this Hilbert space, you have, for example, your observables being operators, okay, acting on this infinite dimensional Hilbert space. Okay, I will not say too much about the rest. Okay, I think probably the last one is actually it's not considered as a postulate by many other researchers, but in the book of Tai Wu, I don't know how he pronounced this, perhaps that's wrong, but he include this idea of a CCR postulate. And in fact, if you look at the case of the quantization that people do in general, in the end, they will have to refer to this CCR postulate, which is actually telling you about the commutation relation between position and momentum. Okay, and it's given by this Heisenberg-Weil algebra thing. So whatever you do, okay, you want to generalize certain things, but you have to end up with this basic fact that has to be no, true if you want to describe quantum mechanics. Okay. Yeah.
Tensor products based thing.
Okay. Some people add this to be another additional postulate. Okay. So I did not put that in. I mean, some people do a lot more postulates there, but again, I'm just taking the basic ones. Okay. So you can think of your tensor product just enlarging your Hilbert spaces, really. In the end, whatever it is, you have to consider what is the configuration space that from where you build up all these wave functions, okay? And then your configuration space will involve these coordinates for positions, and then you have your commutation relations, okay? Does that answer your question? So in the case of say a two particle Hilbert space, then you have the position of two particles instead. Okay. So no, this is funny. Sometimes we do all these calculations in finite dimensional states. We tend to ignore what actually happens physically. Physically, there is this position that we have to take into account. So, for example, when we talk about Bell's inequality, the fact that you can't have no, you talk about positions of these say two entangled particles, okay, and how you actually recognize that the position of two entangled particles will require you to have the positional aspects of the Hilbert space. So you can't run away from it. Okay. All right. So this is the thing that I mentioned just now. Your CCR is actually in a new paper by Tobias Fritz. I think some of you might recognize the name. He actually considered that the CCR that you actually have is actually a witness to the dimensionality of the Hilbert space. In this case, would be infinite dimensional. So whatever you try to do, then you'll find that you can always, you can make approximations, but in the end, you'll get to the point of, you have a Hilbert space which is quite large. Okay. So you can read the paper if you want to. Okay. It's 2013 paper. Okay. And to tell you some of the subtleties that I mentioned in the abstract of my talk, so, which I did just without really thinking about it. Okay, there are problems with respect to this. For example, when we do sort of finite dimensional cases, we think of matrices as operators. Okay, so in the trace of a product of two matrices, your trace AB equals trace BA. So if you impose this cyclicity of this trace, okay, then your commutator will have a zero trace. And that cannot work with your CCR because your commutator is non-zero. So in other words, somehow the position and momenta operators are not quite included in the so-called trace class operators that people normally talk about. Okay, these are compact operators whose trace is actually finite. Okay, so the other thing about these infinite dimensional Hilbert spaces, you require other properties like completeness. So that means you can always define the limit within the same space with respect to a certain norm. Okay. So there must be a way how you get the norms, and this is not trivial, okay, because essentially you're talking about infinite dimensional space, okay. And then the Hilbert spaces must be also separable. That means you can actually find a countable number of autonomous bases. Now, why is that good? Because then you can actually do some approximate functions to your wave functions. Okay, so this is actually good in realistic calculations. Okay, and then when you have these infinite dimensional spaces with all these properties that you need to look at, okay, the completeness and the separability, one should ask, okay, just like manifolds, for example, you have a model space. The manifold model space can be Rn or Cn, for example. What would be the model space for the Hilbert space? So these are, no, there are many different, okay, forgotten to put the footnote, kind of putting a superscript. So this superscript is, this 10 is actually referring to this. So you can look up that Wikipedia page and you can find all these different spaces that can become the model for your infinite dimensional Hilbert space. Okay. So with respect to this completeness, and no, it requires you to have the idea of convergence, for example, and there are many different convergence that you need to consider, and this goes back to the fact that you have to define a norm, okay, and then what kind of topology that you're it has to be continuous in the sense of referring to a certain topology, and these are normally we tend to ignore this stuff because nobody wants to be bothered with all those details, but those details can be problematic when you use your Hilbert space wrongly. We shall see a few things. One of the things that you already seen is the case of the trace. Okay. So this is going to be short, right? I'm going very fast. Right. Okay. With respect to the infinite dimensional Hilbert space as well, one of the things that Dirac postulated was the delta function. Okay, so your delta function integrates to 1, but yet in terms of the formal definition, it's almost it's 0 almost everywhere. And then when it is integrated with another function, it gives you this value at a particular point. Okay, and this is not quite a function, and the theory itself was not really formalized until probably the first one would be Galvan, I think, who does that in terms of a generalized function, and then Schwartz after that defined in terms of distribution. Okay. Now, why is this delta function important? Because one considers that usually in terms of your position operators, and your delta function is like your eigenfunction. But remember, the way we understand this eigenfunction is with respect to an integral over over some domain in this particular case. So you can see here, x delta x phi, it has to be integrated with this test function in order for you to get this answer, okay? And then this can be thought of the same what I call the same integral, but with the eigenvalue x naught coming out from there. Okay, so two things. First, it has to act on a test function phi, and this test function phi has to be well behaved in some way. Okay, so and then when you integrate it, you get a number. Okay, essentially, and then one can think of that to be as a linear functional of the original function, okay, and because of that one needs to define it slightly weaker from the case of the normal operators that you normally consider for your Hilbert spaces, okay. So your domain of your position operator is normally considered as a Schwartz space. These are just functions, and of course there are derivatives which are rapidly rapidly decaying, okay. And then your generalized function, in this case your delta function, will belong to the dual space of this Schwartz space, okay. So, and the relationship, you can see that this is your dual space of the Schwartz space. Your Schwartz space is actually just a subset of your square integrable functions, okay. And this actually means that the dual space is bigger than the Schwartz space itself, okay. So this in a way tells you there are more things inside the dual space compared to the original vector space, okay. And sometimes we call this tree to be a Gelfand triplet, or sometimes it's called a Rig Hilbert space, just in order for you to allow this idea of generalized function or delta function to be inside the theory. I think I'm beginning to, is this this 7? Okay, it's going to be very quick here. So, of course, like I said before, there are some subtleties with respect to what you assume as your Hilbert space, or in this case, sometimes you assume the Schwartz space. Excuse me. So you can consider this as just a problem that I picked out from this paper of Ranade, okay, where you consider a particle in a box, okay, and essentially you can use this particular function which is defined in the box, and you can actually show that your Hamiltonian square, okay, acting on this wave function is actually equal to 0. So what actually happens in this particular case, then if you try to look at the squared uncertainty, okay, deviation from the mean, which is actually given in terms of expectation value of the h squared minus expectation value of h squared, you'll find that this is 0, and then this is going to be positive. So in other words, your h squared is actually negative, okay. So here is again the fact that we assume that you can actually do this throughout the whole real line is the problem, okay. So one can actually try to look at another paper which is actually in American Journal of Physics. Is quite instructive, and you have even a problem of how to define an operator to be self-adjoint, okay. So you can have a look at those papers. But one's probably more of interest to us is when it comes to, say, angular variables. And if we try to impose, say, the canonical commutation relation, okay, phi j I h bar, just like qp equals to I h bar, you know that this doesn't actually work, okay, and essentially, these are well known to people in quantization. You need another group to actually dictate what kind of commutation relation that you should have here. If this do work, and some people do this, okay, if this do work, then it actually corresponds to a continuous spectrum and not a discrete spectrum for angular momenta. So that is actually wrong. And there are many papers that talks about phase and angle, so angle and I can't remember angle phase thing. Okay, I can't remember what they do in quantum optics. Also have all these kind of problems coming in. Okay, so if they are not careful, then you get nonsensical results, and these are things that people has pointed out in the research papers throughout. Okay. But the basic idea is the following. Point spectrum, which is essentially discrete spectrum, always refers to some compact domains. Okay, and when you have continuous spectrums, then one needs to refer to some kind of short space. So you can't just simply assume things, okay, you can have it square integrable functions on some space and then you think it's okay. And this is problematic because you would think, for example, when we do quantization on some cotangent bundle configuration space, you know that this is non-compact. Okay, so this will be some q times the fibers. Okay, the fibers will be actually non-compact. Okay. There might be some twisting as well. So in other words, one has to be careful how you construct the wave functions. And in fact, in the what you call papers, the early papers of Ashteka and his student, okay, one of the main concern is how to build up an inner product space. They have another reason why this is supposed to be, because they are talking about Ashteka variables. Okay, but the idea is, okay, it's not as simple as just saying, okay, I'm going to have square integrable functions. No, irrespective of what's going on. Okay, so there are problems. Okay. So so that is essentially, I think that's it. Huh? I'm getting to my second last slide. So one of the things that probably no one should worry is the kind of structures that one assume to build your Hilbert spaces. So these are things that people are considering. Things like where is it? So you talk about topological vector spaces, metric spaces, and then measurable spaces. So talk about what measures you're going to take. Okay, and then this also relates to what I mentioned earlier about von Neumann's idea to look into operator algebras. Okay, and one should be very careful when one deals with abstract structures like this, so that you don't go overboard with assuming certain things which actually doesn't happen. Okay, so these are just my precautions of to anyone so interested in this area. Okay, so I think that's probably it. So sorry, it's only a short thing. I was hoping that I could get into some C-star algebra thing. Why does one element consider a specific type for the one element algebra? Okay, that's it. So I hope I didn't let anyone down. This is what I can prepare from previous yesterday's afternoon until now. Okay. I do a lot of reading,
Your
but
question.
pardon? A question? Yeah, sure. Yeah. That's dependent on the problem. Yeah, yeah. As far as I know, uh, there's no universal thing that you can actually do. You have to go back to what's been what's the assumption there. Uh, Whether you use say a real variable or complex variable, actually changes a lot. So you can't just simply think that okay, I'm going to use square integrable functions. That is the thing that people do most, right? They think that square integrable functions answers everything. No, it's not. Any more questions? There is one paper that I was hoping to read before that, talking about universal models, but I didn't get to read it. It's too technical for me. Even in the case, one of the things I realized this actually when I did my PhD, when I had to do loop groups, okay, for my PhD, and then I look it up, and then there are various different things that you can actually do, and you have no idea where to start. Quantum field theory is much worse. Oh, rumah dalam kereta. Oh, ini lagi hebat. Yeah, but okay, as I said, no, one has to come back to the original thing. Okay, essentially, you look at the configuration space. You want to build wave functions. Okay, so the wave functions has to stay somewhere. Okay, so you just cannot just pick a symmetry group and say, okay, that's it. No. So this is the problem with certain quantization school. You want okay, they don't care where the space, where the original space lives. Of course, if you want to make it just a mathematical game, then you can.
Yeah. So if we're going to use this functional analysis, then we go back to all this, starting from understanding the measurable side, and then
Yeah.
build out the same practice that I have.
Okay, so you should tell us more. Yeah, how what measures that you're going to take and so on and so forth. Those are those are things
You know,
that I've never touched in
yes,
the past. See.
yeah, because but I'm trying to uh, go for trying to avoid this measure theory at some point, because actually we can go by some structure, but it takes some time. So
Yeah, again, what I'm saying here is probably no. If you really want to have some physical meaning towards what you're doing, if you're thinking in terms of no, okay, I'm just doing maths. No problem.
yes,
Okay, if you're trying to describe physics, then no, consider all those. So even quantum field theory, there are so many problems still. No, it's still open. Mathematicians are looking at it.
yeah, maybe I should go back to my Lebesgue measure and present
Yeah,
something.
I wanted to mention all this measure theory. So what's a Lebesgue measure?
It's more, well, the first thing I learned about measure is just computing a distance. It's like a set,
Yeah.
okay? So it's just well, from my late supervisor, everything's like, hey, very simple. Measure, measure theory is just distance. You see, when you say something like that, but then when you go into proving things and solve few things, sometimes it doesn't speak to us. Especially the books are from mathematicians, right?
Yeah.
So
But,
you
but,
don't
but there's
say
a crucial difference, right? Between the
very crucial difference
Riemann measure
between.
and the Lebesgue. So
Yes,
the
yes, yes.
so
Yes,
the
exactly.
yeah, the Riemann is actually a partitioning of your domain. Your measure is your codomain.
They're
Yeah.
general than the Riemann measure. So the Lebesgue measure, that you have the Lebesgue integral. So then you have a few Nicodemus theorem. I remember this name for quite some time. So you can prove all the measure that you will do when you integrate. So remember, for the probability density actually comes from this, having the measure comes in. So yeah, I think that's the crucial part.
The other point, probably, I wanted to say this, but I'm not saying this in a sense that, okay, I'm criticizing anyone, okay, but no, when we talk about all this non-commutative geometry thing, there are a lot of this idea of operator algebras and measure theory inside there. See, if you look up the book by Alan Kohns, you you know where he starts. And then the other thing that probably one needs is essentially theory of fiber bundles. Okay? So these are things that at some point I wish I could have done things a little bit more detailed in a way, because I think those aspects are much more difficult to consider. Because when you talk about, say, doing representation of certain groups uh, on the Hilbert spaces, I mean, these are things, whether it's going to be a sections of some kind of bundle thing. These are things that lot of things to learn. So I'm not quite sure. Part of this exercise of doing this talk is actually for the USM talk. The USM talk is even worse because I have to talk about the whole of mathematical physics.
Oh, so this is like a pre coffee talk.
Well, I mean, it's like getting myself prepared. So, but again, I think we are lacking in this part of functional analysis. I think probably we do not want to be mathematicians, but we should be aware. One of the things that one of the mathematicians was saying something about physicists, saying that, see, they can talk about anything. They don't care whether it's well defined. No.
The physicists will talk to the functional analysis like this. Well, the functional analysis usually is too detailed.
No,
Usually,
actually, that one has to strike a balance, because some of the, like existence, for example, that okay, there is just physical phenomena that you're supposed to describe. If you want me to say that something exists, that's the physical phenomena that tell you that it exists. But it's just a matter of how you're going to write it down mathematically.
so
So,
true.
okay. Anything else you want to discuss before I end this recording? Or should I end it now?
You can edit now. Oh, is there any other questions?
The problem with this recorder that I have to sort of shut down because